Okay, this is problem 6 from the AP1 forces packet, and we've got a box that is going to have an initial velocity of 2 meters per second, and it's going to hit this ramp, or this inclined plane, as they're called, the fancy name for them, and it's going to slide on down, and when it reaches the bottom, it's going to have a different velocity. And we can tell that it's going to speed up because that's what happens when things fall downward, they speed up. Lucky for us, it says right here in the problem we can neglect all frictional forces, which means there's no friction anywhere in the problem. So we don't need to worry about friction. It doesn't exist in this problem. And so all we need to worry about is what's going to happen to the box as it slides down this ramp. And so gravity is going to speed it up, and we're going to figure out how much faster it's going to be at the bottom. And so I'm going to start this problem the way I start every problem. I'm going to draw a force diagram, or a free body diagram, for the box. And if there's no friction, nothing's going to change about its velocity while it's on the flat part here. It's not going to start speeding up until it hits this hill. Then it starts speeding up, and then once it hits the bottom here, it's going to stay at whatever speed it landed at the bottom here the whole time, because there's going to be no friction to slow it down, and there's no gravity to speed it up anymore, so it'll keep that consistent speed the entire time. So let's go ahead and draw a force diagram. And so we're on a slope as we go. Well, that's an ugly box, but oh well. And we have a box that it doesn't give us a mass anywhere for the box. And so I go ahead and leave it as M, a box mass M, if I don't know what the force on the box is. And then I'm going to label my forces. Remember, when you are on a hill, the force that's going down or pulling it down the inclined plane is going to be that sine component of gravity. So gravity times the sine of your angle is going to be the force that's pulling it down the hill. And the force, the one that's parallel to the ramp. And the one that's perpendicular to the ramp is going to be that mg cosine theta. And this is the short way to do it. If you remember these two, if you can remember that this one pulling it down the hill is mg sine, and this one perpendicular is mg cosine, then you don't have to solve for it every time, and it makes your life a lot easier. And so the other forces on the hill, it is sitting on a hill, it's being pressed by the hill, it's a surface, and so it would be this normal force. And there would be friction going back up the hill, but it said in this problem that we don't have to worry about friction. So we are not going to worry about friction. Okay, so once the box is on the plane, you have to ask yourself, how is this box moving? Is it moving parallel to the plane only, or is it moving perpendicular to the plane? And hopefully you can see that it's not flying up off the plane or burying itself into the plane, and so these forces are going to be balanced. They're the only two forces that are perpendicular to the surface, and so they have to cancel each other out. And so if you want to remind yourself, you can say that the magnitude of this force is going to be mg cosine theta as well. These are going to be balanced out. They're going to be equal to each other. And that's pretty much it if there's no friction. And so then you would go ahead and you want to find out what the acceleration of the box is when it goes down this hill, and so, or this ramp, this inclined plane. There's 3 names for it. Great, right? And so what you're going to want to do is you're going to want to do Newton's second law, as always. So you have these two forces cancel. This is the only one left, and so your net force for this particular case is going to be mg times the sine of the angle. We know the sine of the angle, but we don't know mg. Oh, we don't know m. We know what g is. G is 10. We also use Newton's second law. There you go. And so when you set these equal to each other, you get mg sine of theta equals mass times acceleration. And you notice that you can cancel out the masses. Anything that shows up on both sides of the equation and every term of the equation, you can cancel out. You don't need it. It's the equivalent of dividing everything by m. And that's okay in algebra. You can do whatever you want as long as you do it to everything in the equation. So if we divide both sides by m, then we can cancel out m. We don't actually need to know it. And so g sine of theta is going to be equal to our acceleration. And we've got these things. We know what g is. G is going to be gravity, and I'm going to use the magnitude of gravity. We always use -10, but in this problem, I'm going to consider down this ramp to be positive, and so it's going to speed up, and so I'm going to make my gravity positive. I'm going to use the magnitude of it, because, like always, negatives mean direction, or positive negative means direction, and I'm going to consider everything this way down the ramp to be positive to make my life easier. And so I'll do 10 times the sine of 36, and that's going to equal my acceleration. And when I punch that into the calculator, I should get an acceleration of 5.88 meters per second squared. And so that is the acceleration of my box as it goes down the ramp. And in order to figure out the rest of it, you need to know how long is this thing accelerating for. And by how long, I mean what is this distance that it's accelerating for? Because we've got an acceleration, we've got an initial velocity, we're looking for a final velocity. This sounds a lot like kinematics. And if we're going down one slope with one angle, then it's going to have one acceleration, which we just found. And so we can go, once we've got that, we can go ahead and use kinematics. We can say the initial velocity of my box is going to be 2 meters per second. The acceleration of my box is 5.88 meters per second squared. We're not sure what the displacement is yet, but we would like to find the final velocity. And so we're missing the displacement of this box, and the displacement would be how big is this ramp? How long is this ramp right here from top to bottom? Because that's the part where gravity is going to speed it up. Anything that's a flat surface is not going to speed up this box. Fortunately for us, they gave us this, which is the height of this. And so we can use our knowledge of trig to figure out exactly what the slope is. If we just turn it into a right triangle like that with 36 degrees, and this is going to be 1.5, and we would like to know what is that? What is the hypotenuse of this triangle? And if you pick out the right trig function, you've got the opposite. You want to know the hypotenuse, you've got the angle, you're going to be using sine. So sine of 36 equals your opposite divided by your hypotenuse. And remember, whenever you're solving for any variable that's on the bottom of the fraction like this, the easy solution is to have it just switch places with whatever is on the other side of the equal sign. And so this will end up being h equals 1.5 divided by the sine of 36. And we can punch that into the calculator, and we can get a height of 2.55 meters, which is going to be my displacement over there, 2.55 meters. And now that we've got three things, we can solve for the fourth one. No problem using kinematics. You would use final velocity squared equals initial velocity squared plus 2 times a times delta x based on the information you've got. And you would go ahead and solve for final velocity. You've got an initial velocity of 2 and an acceleration of 5.88 and 2.55, and I'm running out of room, is going to be my displacement. And when you solve that, at least when I solved it, you should end up with 5.83 meters per second squared. Meters per second, not squared. And so that would be the final velocity of my box when it reaches the bottom. It sped up while it was on the hill, and then it stopped speeding up when it was, once it reached the bottom because there was no friction. This problem would be a little bit tougher if there were friction, especially if there was friction on the top and the ramp and the bottom. Usually problems like this, they'll say there's only friction on the ramp, maybe, part of it, in which case you would have to go and add a friction force in here. But that wouldn't be too much harder, because if I added a friction force in here, I could solve for it, and then I would use the friction and the mg sine theta part to find the net force and get the acceleration from that. The rest of the process would be the same. Fortunately for us, anytime they say neglect all friction forces, our problem becomes a lot easier, and we can use this approach. Anytime you're on a ramp, you're going to use this right here. You're going to use mg sine theta, mg cosine theta, and your normal force will be balanced with mg cosine theta, unless for some reason you're flying off the ramp or plowing into the ramp. Other than that, it's always going to look like this, and if you just go ahead and memorize this, then these ramp problems become a lot easier.